So here's the plan today. First, I want to go over a little bit about the question we finished on last Wednesday's class. And then we're going to begin a new section, and then I will review for the first meeting. So at the end of the last meeting we had, we were talking about this function. So x squared plus y squared minus 6y plus 9. So this is our f(x, y). And instead of having the whole new plane as our domain, here the domain is restricted to x squared plus y squared is less than or equal to 25. And we also agreed the domain is a closed disk. And by closed disk, I mean the interior of a circle with radius 5 and center is 0, 0, including the boundary as the circle. Right? So the disk is a solid region in R2. Are you with me? So we have to agree on these terminologies. A disk is a solid region. A circle is a curve. Right? So a disk is essentially a two-dimensional object, and a circle is a one-dimensional curve. So this is our domain. And as we discussed, finding the global and global maximum and the global minimum, in order to find these values of the function, we begin from the interior where we have to find the critical points. All right? We find the critical points, and then we classify whether it is a local maximum or local minimum. And then we go to the boundary and see whether there's any maximum or minimum happening on the boundary of the region. Okay? So this is how we find all the possible things. So first is a local maximum, minimum in the interior. So basically, this is what the usual critical points plus the second partial derivative test. Okay, and then we have to go to the boundary, which in this case is just the circle. All right. So you find all the possible maximum and the minimum values in the interior, and also the maximum and the minimum value on the boundary. So the global maximum will be the one you choose from all the possible candidates here. All right. You choose the greatest value among these values, and then the global minimum will be the smallest value you choose from the possible candidates right over here. All right. So we spend quite some effort to find the first possibility, which is the local maximum minimum in the interior by critical point in second order derivative test. And they are pretty easy for this case, as we already found the local maximum and the minimum in the interior. What's the critical point we find? X is equal to 0. So it's 0 and 3. So the function value at the 0 of 3 is equal to 0. Okay, so this is what we have in the interior. And then going into the boundary, I need to find the corresponding function, right? Because it is a one-dimensional object, I have to reduce the function from 2 independent variables to 1 independent variable, right? And the equation for the boundary is actually x squared plus y squared is equal to 25. So essentially, you try to find the critical points, not critical point, you want to find the function, this one, with restriction such that x squared plus y squared is equal to 25. You need to reduce one variable, all right? So what we did here is we just simply replace x squared by 25 minus y squared. Okay. So what we did here is this function will be 25 minus y squared plus y squared minus 6y plus 9, which is essentially just 34 minus 6y. And then I said I have also got a restriction for y, which is between 5 and minus 5. Some of you are not quite clear about why this is the restriction for when we reduce the variable from 2 to 1. Okay? So remember, this is our domain of the 2 independent variable case. All right? So x, y can be freely changed within this closed disk, which means x has to be restricted from -5 to 5. And y has to be restricted between -5 to 5 as well. All right? Because these xy's can only be changing within this closed disk. Even though I'm reducing this function from 2 variable to 1 variable, I still have to follow our original domain right here. Know what I mean? I still have to follow this original domain. That's why I have the restriction y is between 5 and -5. Do you agree with me? So this is why I have this restriction for 5 and -5 for y, and I'm only looking at a linear function. For linear function, the maximum and minimum value have to achieve at the endpoints. All right? If the linear function is increasing, then the left endpoint is where you achieve the minimum value. The right endpoint is where you achieve the maximum value. If the function is decreasing, the other way around. All right? Yeah. This, in terms of y, is decreasing, so the maximum value is achieved at the left endpoint, and the minimum value is achieved at the right endpoint. All right? So basically, I just need to compute. So if I rename this as a new function g of y, g of -5 is equal to 34 minus 6 minus multiplied by -5. So this is giving me 64. And g of 5 is equal to 34 minus 30, which is equal to 4. Right? So on the boundary, 64 will be the maximum value, 4 will be the minimum value. So if I want to find global maximum and the minimum, I need to choose from all these possible candidates here. The only thing I need to do in the very end step is to compare 3 values, 0, 64, and 4. All right? So the maximum value is 64. It is achieved on the boundary. More specifically speaking, it is achieved at a point 0, minus 4. So 64 is the global maximum at the point. If I have to go back to the original question asking about the global maximum and the minimum value for these 2 independent variable cases, I need to find the point where the function will achieve its maximum value, and this point has to be a pair of numbers. All right? I know it is happening when y is equal to -5, and when that happens, x has to be equal to 0, which is right at this point. Right? So this f of 0 minus 5 is equal to 64, and we can also say 0 is the global minimum at the point 0, 3. So if I go to 0, 3, it's going to be right here. So this is where the function value is equal to 0. Okay? Okay? So if you don't have any restriction on the boundary, okay, if your domain for 2 independent variables is all the 2-dimensional plane, you don't have to worry about the boundary case at all. So what you do is just go strictly for the first order derivative equal 0. That's where you find the critical points, and then using second order derivative test to see whether this critical point is where you achieve the maximum, minimum, saddle point, and not conclusive. Are you with me? So there are 4 different cases for using second order derivative test. So you're having your first midterm on Wednesday. This is definitely going to be there. Right? So this is definitely going to be there. So any questions you want to ask for? This is the nicest application you can find for partial derivatives, right? For instance, if you're given this kind of function, there's no way for you to even attempt to find where the function can be maximum or minimum. So the partial derivative test is a very, very useful tool to locate these extreme values. Yep?
So in this question, the domain is given?
Yeah, the domain is given, exactly. The domain is given, so this is the domain.
How did you know that 0 was the global min?
That's a good question. That's a very good question. Okay, so so a very strict justification will be the following. Okay, if this global minimum is achieved in the interior, it has to be a critical point. All right, which is right here.
Okay.
If it is achieved a boundary, it has to be only 4.
Okay.
follows me? Which means if it is global maximum, either it is interior, which case it has to be a critical point, and the smallest value I can achieve is 0. Or it is on the boundary, the smallest value it can achieve is 4. So if I combine all the cases, the only possible for the global minimum to be achieved is right at this point, right? So if you want to justify it in a more strict sentences, that would be the cases. Questions? Yeah, right.
We didn't have to use the second partial derivative test? Or?
Oh, okay. I did use the second order derivative test, strictly speaking, for this 0 to see whether it is a minimum or maximum. But because I want to find a global maximum and minimum for the whole domain, I only need to go for these 3 different values because they are the only possible candidates. These are the only possible candidates. To be a global minimum in the interior, it has to be a critical point. But there's only one critical point. You can, in fact, use the second order derivative test to see whether 0, 3 is a local minimum or maximum. In fact, we can do that. Let's just do that. So if I have a second order derivative matrix, what I have is fxx, fxy, fyx, and fyy. So let's see what I get at the 0, 3. So fxx is equal to 2, 0, 0, and 2. Am I right? So this is a positive matrix. The determinant is positive. Fx is also positive. So by the second order derivative test, this is exactly a local minimum. Right? This is the exact local minimum. And so, say, by second order derivative test, the 0, 3 is local minimum. But I have to say I'm guilty in saving a lot of sentences here. Strictly speaking, I should write down all the name right here. And 0, 3, strictly speaking, should be the point where the function achieves its local minimum value. Okay? So strictly speaking, it's much more precise you can make. Questions? Okay. So a typical question I can give you in terms of this partial derivative applications. I give you a function, and I need you to find all the critical points and classify these critical points. By classify, I mean using the second order derivative test. Okay? Questions? Okay, so I still have to cover some new material in chapter 14. However, this is not going to be in the midterm. Okay. So as we discussed in the very beginning, there are 2 main topics for multiple calculus, multivariable calculus. Multivariable derivatives, that's where you take the partial derivatives, okay? And the multiple integrals. So this is our second major topic for the whole semester. And first warning I gave you is this is going to be more difficult than the partial derivatives for a simple fact I will explain right now. So if I want to generalize the derivative from a single variable case, so if I have a single variable function, so I have a derivative, the usual derivative prime of x. All right? Remember, when we have a function involving 2 independent variables, we can generalize this derivative to 2 partial derivatives, fx and fy. All right? So fx and fy. So the derivatives are basically talking about a rate of change. Right? So if you change your independent variable a bit, how much the dependent variable will change. So strictly speaking, the generalized partial derivative for 2 variable cases are not these 2 partial derivatives. It's really the directional derivative. Right? So the real generalization for the usual derivative to multivariable case is not really these 2. It's really du of f. Right? So this guy is really the generalized form for rate of change. Because if you have 2 independent variables, then the domain is going to be the region in R2, we change the dependent variables in a direction by a bit, and we compute the rate of change. All right, so this guy is the real generalized partial derivative coming from the single variable calculus. And the complexity comes from this direction can be chosen arbitrarily. All right, so if you only have one independent variable, you're only choosing on the real line, either you move right or you move left. That's the only two possible directions to go. But if you're on R2, you have so many different directions to change your independent variables. All right, and in fact, we can classify and compute all the directional derivatives once you fix a directional vector, right? So generalizing from a single variable derivative to multivariable derivative, the complexity comes from the direction where you can change your independent variables. Are you with me? So you have to understand the difference between these two settings. However, the nice news is when you compute the partial derivatives, all the things are exactly the same. All right? Computing the partial derivatives, no matter it's directional derivative or these guys, are just a single variable calculus. You're freezing one of the variables you're computing against the other one. However, if I'm taking the integral of x dx, so the single variable integral, if I want to take an integration of a function, I have to have two pieces of information as well. Okay? Here I have to have two pieces of information, the function and the direction where I'm moving my independent variables. If I'm taking the integral of a function, I have to have a function and an interval. All right? So this is actually the integral of a function f on a closed interval ab. All right? So basically, if I want to compute an integral of a single variable calculus, I have to have a function with one independent variable and the integrating region as an interval. Again, in a one-dimensional case, the integrating region is extremely easy. It's just an interval. You don't have to worry about any complicated cases. However, imagine if I'm taking a double integral of a function involving two independent variables. This will be the general form. This means I'm taking the double integral of a function involving two independent variables on a region R in R2. All right? So if we're taking the double integral, we still have to have two pieces of information, the function